Hello AP students. This is going to review some probability for the AP Stats test. By no means is this inclusive, but I figure it's a good review, and I'm going to try to throw some medium to hard style problems at you here as well. So I'm going to cover a few things in this video. Number one, definitions. Then we'll get into the addition rule, multiplication rule, and then we'll look at binomial and geometric probabilities. Alright, so let's start with some definitions here. So we start out with the sample space of a probability event, and a sample space is the set or list of all possible outcomes. So everything that could possibly happen is part of the sample space. We also have when we have two events, we always need to recognize if event A and event B are independent or not independent. And again, independent is going to mean that the outcome of event A will influence the outcome of event B. In other words, it's going to change the probability. If event A happens, does the probability of event B change? If not, well, for the independent multiplication rule, we say that the probability of A and B is going to equal the probability of A times the probability of B. And for dependent events, we say that the probability of A and B is going to equal the probability of A times the probability of A, times the probability of B, given that A happened. And I touch on that again in just a little bit. We also had mutually exclusive. Events A and B are mutually exclusive if they cannot occur at the same time, simultaneously. So that is that the probability of A and B both occurring is 0. Like the probability, like being a junior or a senior is mutually exclusive because you cannot both be a junior and a senior at the same time. At least I hope not. Okay, so let's try a problem of this. So we flip a fair coin 3 times, list the sample space. So there's a couple ways to determine the sample space. I think the best two ways are either a tree diagram or using something like a two-way table. In this case, tree diagram is going to be better because we're going to be doing this 3 times. So if you weren't sure how to make the sample space, you could just start listing all possible outcomes, but it's easy to get confused. You can kind of go, hey, first flip I can have a heads or a tails, and then if I got a heads, my next flip I could get a heads or a tails, or if I got a tails the first time, I could still, my next flip, get a heads or a tails. And then one more time here, we'll do one more iteration of this. Heads, tails, heads, tails. I'm going to go over here because I'm running out of room. Heads, tails, heads, tails, heads, tails, heads, tails. Now this is going to give us the sample space if I follow each one of these branches of the tree. So following the top branch, that's getting all 3 heads. Then I get heads, heads, and a tails. Then I get heads, tails, heads. Then I get heads, tails, tails. And there goes all my heads on the first flip. So I could also get tails, heads, heads, tails, head, tails, 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 head, or lastly, tails, tails, tails. So with a fair coin, you're equally likely to get a heads or a tails. That also means that I'm actually equally likely to have each one of these outcomes here. But again, that's only in the case of a fair coin that's 50-50% that I'm equally likely to get a heads and a tails. So question, what's more likely to occur? Getting heads, 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 or tails, head, tails? Oh, they're equally likely, are they not? They are equally likely, so they're equally likely. And why are they equally likely? Because I'm talking about respect to order here. Getting 3 heads in a row is the same exact probability of getting exactly in this order a tails, heads, and then a tails. Now yes, it's true, I am more likely to get 2 tails than all 3 heads. And in fact, it doesn't take me very long. I could look at my sample space here and go, how many ways are there to get 2 tails? Well, that way, that way, that way, and that way. 3 out of 8 ways there are to get 2 tails. But I'm, again, looking specifically at tails, heads, tails. That's that one right there. That's just as likely to occur as are all three heads. All right, let event A equal a heads on the first flip, and event B equal flipping two tails. Again, we're talking about three flips of the coin here. Are A and B mutually exclusive? Are these two events, getting a heads on the first flip and flipping two tails, total out of 3 times, are they mutually exclusive? Can they occur at the same time? Can I get a heads on the first flip and eventually flip two tails? Yeah, I can, right? Specifically if I get a heads, tails, tails. So can these two events occur at the same time? Yeah. So are they mutually exclusive? No, they are not mutually exclusive. Events are mutually exclusive when they cannot occur at the same time. So they are not mutually exclusive. I'm going to abbreviate that one. Okay, there covers our definitions. I would like to mention there's a couple of definitions I went over. Didn't cover things like the complement of event or conditional probability. We'll see those in a little bit as well. Okay, first rule is the addition rule. And we say that the probability of A or B, remember this U symbol right there means union or. This symbol means intersection or and. So the probability of A or B occurring is the probability of A plus the probability of B minus the probability of A and B. And in fact, if A and B are mutually exclusive, then the probability of A and B happening is 0, so that shortens to the probability of A or B equals the probability of A plus the probability of B. This is for mutually exclusive events. Probably not going to look into those too much, but we do want to look at the not mutually exclusive events. Some tips on this is to make a Venn diagram. If you guys typically remember here. So here's a Venn diagram, here's our intersection. Everything inside the box is the sample space. So this is the sample space, everything inside. Now, this whole region in here we're going to call set A, and then this whole region there we'll call set B. That's the entire circle. They intersect at A intersection B entirely. I'm going to switch colors here. Entirely the whole thing. That's the two circles together. If you're in one of those two circles, you're either in A or B. And if you're here, not in either, then there's two ways of saying that. You're either in A complement the intersection of not in A and not in B, or you're also in the complement. You're not in A or B, so that's A union B complement. That's in fact, those two are equivalent, and that's something called De Morgan's law that we don't cover in this class. I'm going to get into two-way tables. I actually like two-way tables better than the Venn diagrams, but the AP board tends to push the Venn diagrams, so we're going to do two examples, one with a Venn diagram and one with a two-way table. Alright, so there's 130 students in a lecture hall. 85 have a laptop. 120 have a mobile. 5 have neither. How many have both? Ooh, it's crazy. So here's my Venn diagram, and okay, it's not the prettiest Venn diagram in the world, but I've seen worse. So the sample space here, how many is in everything? Everything needs to add up to 130 because there's 130 students. Now I'll call this L for laptop and this one M for mobile. So this whole circle of laptops here is going to have to equal 85. This whole circle is going to have to equal 120. Well, let's see what we have. We have that 5 people have neither. So what does that mean? How many have both? Well, I'm sorry, how many have either or? Let's put it this way here. How many have either or? We know together there's got to be 125. How did I get 125? Because 5 people don't have neither. So that's going to leave we're going to know that I'll just call this A union B. A union B has to equal 125. Let's see if I have enough room to write here. I'll switch colors. So if you want to solve this algebraically, some students are a little bit more algebraic minded. But let's see. So the A union B should equal the probability of A plus the probability of B minus the intersection. So right now I have that 125, that's A union B, is going to equal 85, because that's how many, that's say the probability of A, or in this case having a laptop, plus 120, that's how many had a mobile, minus, I'll call this X, the intersection that I'm ultimately solving for. So it's going to give me 205 over here. This is going to equal 125 minus X, and a little bit of algebra. You'll end up doing 205 minus 125, and it should be 80, but I'm just scared that I'm checking it on my calculator. Yeah. So X equals 80. So there's 80 students who have both. So again, if I look at this here, if I wanted to complete the Venn diagram, you always want to start with the intersection. So 80 people had both. That's what we just solved for. And if 85 total people have a laptop, well, then there's only 5 people left over here. So those are going to be the ones who only have a laptop. And if 120 have a mobile, 80 of those are accounted for because they also have a laptop. That's going to leave 40 over here. And again, all these numbers, this one and what's outside here, should add up to our sample space, 130. And hopefully I didn't make any mistakes on that one. All right, that one okay? Not too bad. All right, let's try the next problem. In a random sample of U.S. households, 26% owned a cat, 61% did not own a dog, 23% owned only a dog. If we randomly select a household from this sample, what is the probability that they own only a cat? I'm going to use a two-way table here. I like two-way tables. They're much easier, I believe, than Venn diagrams, because you get all sorts of informations. We'll let event D be having a dog and event C be having a cat. This is how we're going to set up these tables. So we have two events, having a dog, having a cat, but each one of those events has a complement. That is D complement, not having a dog, C complement, not having a cat. So I'm going to, one side I'll put dog, not dog, and here I'll put cat, not cat. Now when I add these up, they're going to add up to, depends, you could do this in a decimal, or I'll just do this in percentages. So in this case it's going to add up to 100%. And since these are in probabilities, you could have done the same thing in the last example, but it should have added up to 130 people, for instance. Okay, now let's find out what we have here. Now we're also going to be adding up these margins. So this box, for instance, would be having a cat and a dog. This would be having a cat and not a dog. This would be having not a cat but a dog, and this would be neither having a cat nor a dog. This one here is going to be everyone who has a cat. This one will be everyone has a dog. This will be everyone who doesn't have a cat, and the last one will be everyone who does not have a dog. So when I start putting up these numbers here, I see 26% of people owned a cat. Well, that means that this whole row, because there's two ways to have a cat. You could have a cat and a dog, or you could have a cat and not have a dog. That's going to add up to 26%. Now it says that 61% did not own a dog. Where would that go? See if you can see where that would go on the table. Yeah, right there, 61%. Then it says here that 23% owned only a dog. So that means only a dog and no cat. That's 23. That's going to go right there. That's having a dog and not a cat. Now, everything should fall into place. You may look and wonder how it's going to fall into place, but this is how it's going to work. So if 26% of people had a cat, what percent of people did not have a cat? 74, right? This is going to add up to 100. And same way here, this has got to add up to 100. In other words, 61% of people did not have a dog. That meant what percent of people did have a dog? 39, right? Hopefully, yeah. So from here on out, it's kind of like a Sudoku puzzle. In fact, it kind of started like a Sudoku puzzle. These rows and columns all have to add up to the margins. So if I start with this 23 here, I go, okay, if 23% of people didn't have had a cat but not a dog, let me put it this way, this has to add up to 39. So 23 plus what equals 39? Hopefully my math is okay today. It looks like 16, right? So then 16 plus what equals 26? Hopefully that's 10. That is 10. I can do that one. And lastly, 74 minus 23 is 51. 51% of people had neither a dog nor a cat. So this is what I love about these two-way tables. It gives us way more information really than we had on the Venn diagram, and I think they're easier to solve. This gives us everything we need really for this problem. 16% of people had both a dog and a cat. 10% people had a cat but no dog. That's me. 23% had a dog but no cat, and 51% had neither a dog nor a cat. So just answer the question now. What is the probability that they only own a cat? So that's a cat and no dog. That's going to be 10%. That's the answer to that. I like these two-way tables. I think they're way better than the Venn diagrams. Okay, multiplication rules. Conditional probability, start out with that one. That is the probability of B given A. That's what's the probability of B occurring given that event A has occurred. Well, that's the probability of A and B divided by the probability of A. So it's always going to be the probability of both happening. That's the numerator. And then on the denominator, it's the probability of whatever event was given. I think a lot of times, too, going back to even the addition rule, sometimes the hardest thing, you look at a problem and you're like, well, do I use the addition rule, multiplication rule? So I'm trying to throw in these clue words. Some of the clue words for the, sorry, I did this a little late. Some of the clue words for the addition rule are going to be definitely the word or. That's why I put the word or in quotation marks there. If you see the word or, there's no other formula that we have learned that uses or except for the addition rule. If you notice and is in here as well, but the word or has to be there. Also look for the word neither. Neither could come up. So those are just kind of clue words that should kind of make you jump to the addition rule. And that formula is in the formula sheet for the AP Stats. So some clues to that something is a conditional probability, the word if or given, or maybe of the juniors, what percent, like French fries. I did the independent and dependent rules, but multiplication rules down here. So the probability of event A and B occurring if events A and B are independent is the probability of A times the probability of B. And if A and B are dependent, we're going to have the probability of A times the probability of B occurring given that A has occurred. And sometimes the dependent ones can be a little tricky. Sometimes they're pretty simple. So let's so this is what I wanted to go back with, what we really mean by independent. We say that the A and B are independent if the probability of A equals the probability of A given that B occurred. In other words, that, hey, even though whatever the probability of A happening is, even if event B occurred, the probability of A has not changed at all. I say tree diagrams are probably your best friends for most of these sorts of problems, but not necessarily all. So let's try one. An urn contains three red, 2 green, and 1 yellow marble. If we select 2 marbles at random, what is the probability of having 2 reds, exactly 1 yellow, and at least 1 green? So let's make a tree diagram. At first we could either get a red, green, or yellow. And we can also get a red, green, or yellow. Here we could get a red, a green, or a yellow. But since there's only one yellow first, if we got the yellow, we have this is going to be, we can only get red or green because there's only one yellow. Okay, so I'll start with a kind of dead branch here. I'm going to have a little bit of trouble writing each probability on here. But there are 6 marbles total, so the probability of getting a red is 2 out of 6. Let me change colors on that. So the probability of getting a red is 2 out of 6. The probability of getting a green, excuse me, there were three reds. So the probability of me getting a red is 3 out of 6, or 1/2. 2 out of 6 for the green, and 1 out of 6 on the yellow. But again, so this second draw is technically dependent. The probability that it's red depends on what you got the first time. If you got another red, now you have a 2 out of 5 chance of getting a red the second time, because there's one marble missing total, and there's one red one missing. But for green, there's still 2 remaining. With yellow, there's still 1 remaining. But again, now all my denominators are 5. All right, so let's go ahead and just try to answer these questions. What's the probability of getting 2 reds? Well, the only way of getting 2 reds is if I follow this branch. So that's going to end up being 3/6 or 1/2 times 2/5. So that's going to be 1/2 times 2/5 is going to be 1/5. So I actually only have a 1 out of 5 chance of getting all 2 reds if I pick 2 marbles. Exactly 1 yellow. Ooh, that gets a little complicated now because there's a few ways to get exactly 1 yellow. I could have gotten a red, then a yellow, I could have got a green, then a yellow, or I could have gotten a yellow, and then a red, and then a green. So there's actually 4 ways I can get exactly 1 yellow. And technically those are mutually exclusive, and I have to find the probability of each one and multiply them together. Alright, I'm changing this 3/6 to 1/2 now. So this is if I got red, then yellow. If I would have gotten green, the green 2 over 6 reduces to 1/3 times 1/5, and then plus I could have gotten a yellow and then a red, so there's a 1/6 chance of getting a yellow, and then there's a 3 out of 5 chance of getting a red, and then lastly getting a yellow and a green. There's 1/6 were yellow and 2/5 were red. So I'm going to punch this in my calculator real quick and get you an answer. And all this added up actually to 0.33333. That is 1/3. So that's the answer to that one. At least 1 green. Oh man. Alright, I'm going to skip that one. That one got gnarly with this problem. But see if you could figure that out using a couple ways of doing it. But give that one a try. Okay, let's go on to the next one. Oh yeah, this is what I'm going to be calling the at least one rule. This always shows up on the AP test at least once or twice, and it's always a pretty tricky style problem. So let me give you the at least one rule. What's the probability of getting at least one blah 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 blah? Well, at least one, what's the complement of getting at least one? The complement is getting none. So using the complement rule, the probability of it getting at least one is 1 minus the probability of getting none. So that is the probability that x is greater than or equal to 1 is 1 minus the probability that x is 0. So you roll a fair die 6 times. What is the probability of rolling, excuse me, I forgot the word here, at least 1 3? So you roll a fair die 6 times. What's the probability of getting at least 1 3? Well, the probability of getting at least 1, sorry, that says 3. 3 is going to equal, using the complement rule, 1 minus the probability of getting no 3s. Well, again, this is going to be 6 times now. So what's the probability of getting no 3s 6 times? Well, what's the probability of getting no 3 for one trial? 5 out of 6. But now I'm going to do this 6 times because I got 6 dice. So this is going to be 1 minus 5 6 to the 6th power. and I got 0.6651. Better chance than you thought, right, of getting at least 1, 3. Or maybe worse, who knows. But you try it. Go roll the die 6 times over and over and over, and about 66 or just about 2/3 of the time you should get at least 1, 3. Tricky. So this is going to be a tricky problem. This is a little, you'll see at least 1 or 2 of these style problems on your AP exam. This is technically something we call Bayesian statistics. 6% of athletes use performance-enhancing drugs. I'm just going to abbreviate that, called PEDs. A new drug test can correctly test positive for performance-enhancing drugs 98% of the time. That is, if you're actually taking it, there's a 98% chance it'll come out positive. However, the test yields a false positive result 3% of the time. Don't have enough time in this problem to explain a false positive, but a false positive pretty much means it comes up positive when you didn't take the drugs. So if an athlete tests positive for performance-enhancing drugs, what's the probability that the athlete actually is using performance-enhancing drugs? Oops. Just trying to see if I had room there. Okay, so this is a tricky problem, and let's underline everything that we got here. Okay, so we have 6% of the athletes use drugs, and then it gives us this 98%. Well, what is that? That's a conditional probability, isn't it? That the drug tests can correctly test positive if you are taking the drugs. So you could think of it this way, that the probability that you test positive given you're taking drugs is 98%, or 0.98. However, the test results in a false positive 3% of the time. What does that mean? That means that the probability is going to come up positive when you don't take drugs 3% of the time. So those two numbers were conditional probabilities. Well, what about that 6%? That's just going to be the probability that if somebody takes drugs, there's going to be a 0.06% chance of that. Well, what are we looking for here? If an athlete tests positive for performance-enhancing drugs, what is the probability that the athlete uses performance-enhancing drugs? So can you change that into a conditional probability? What's the conditional probability that we're looking for? Well, we're looking for the probability that the athlete uses drugs given that he tests positive. Okay, I'm going to go a few slides over here. 6%. So I'm skipping through the slides here, but I'm going to recommend a tree diagram for this one as well. And these are just a little tricky to get started. But typically what you want to start with is, in this case, what you were given at first, what percent of people use drugs? It gave us 6%. 6%, right? Sorry, I'm forgetting. Or was it 8%? I think it was 6%. Yeah, thank you. Sorry. So that means how many people don't use drugs? Yeah, 94%, right? Now, whether you take drugs or not, you still have a chance of testing positive or negative. So let's see what all those chances were. Well, it did give us that if you did take drugs, there was a 98% chance that you would test positive. So there's a 2% chance you'd test negative. And if you didn't take drugs, it gave us that there's a 3% chance of getting a false positive. So that means that the test comes out positive when indeed you weren't taking the drugs, so that's going to go there. Hence, there's a 97% chance that if you didn't take drugs, you would test negative, which hopefully is going to be the most likely circumstance. So we were trying to find the probability that somebody takes drugs given that they test positive. So just using the conditional probability, this should be the probability of them taking drugs and testing positive divided by the probability of what was given, the probability that they came out positive. So what I need here is the probability they take drugs and that they're positive. That's going to be my top branch, so I'm just plugging that into my calculator and multiplying those two conditional probabilities, and that's 0.0588. So that's going to be my numerator. Be careful. That answer, I guarantee you, is going to be a sucker answer if this is a multiple choice question. What about the probability that they test positive? Well, there's two ways of testing positive. You could either have taken the drugs and tested positive. That was the 5.08%, 5.88% chance we calculated earlier, or there's that chance of getting a false positive. And if you multiply this branch here, that's the probability that you don't take drugs times the probability that you test positive. If we add that to that, then we're going to get, this is actually saying if I add those two numbers together is that 8.7% of everybody is going to end up testing positive. Well, what percentage of those are actually going to be using drugs? 5.88%. So if I divide those two, I get 67.676. So again, almost close to 2/3 chance. There's about a 2/3 chance that you test positive. Now, if you think about that for a second, yikes, that's kind of harsh. That means if a patient goes in, don't know whether they're taking drugs or not, if they test positive, there's still just about a 1 in 3 chance that they're completely innocent. It's not very convincing, is it? So how good is this particular test? I wouldn't rely on it. I feel like it's a good case for lawyers, right? Bayesian statistics, guys. It's a good branch to study. Okay, almost there. Going into binomial situations, binomial and geometric. So I just want to define again what a random variable is. The random variable x is a variable where x can take on one or more value or values from the sample space. A combination NCR, also written as n over r without in parentheses without a division sign. Well, that's going to end up equaling n factorial over r factorial times n minus r factorial. And I'm not going to get into a lot of time on combinations because they surprisingly don't show up very much. Okay, what is a binomial situation? I think this is going to be the harder part. Here's a problem. Which formula do I use? So you want to use your binomial formula. We'll get to binomial PDF and binomial CDF on your calculator in just a second. If the situation's binary, and binary means it's either a success or a failure. If the trials are independent, one trial isn't going to influence another. That is, the probability of success should always be the same. And there's a fixed number of trials. So I went to bat 5 times. What's the probability I make 3 or more hits, assuming each hit is independent? The formula is on there. It's in your book. It's on, and I say it's on there. It's on your formula sheet. But in reality, your life is going to go a lot faster if you use binomial PDF and binomial CDF on your calculator. Binomial PDF NPR. And N, again, number of trials. P is probability of success. R is going to be finding how many successes. Now, what's the difference between binomial PDF and binomial CDF? Binomial PDF is solving for exactly that many successes. So the probability that X is exactly that number R, the number of successes. Binomial CDF, however, is getting R or fewer successes. So that is the probability that X is R or less. So binomial CDF will always be, the number will always be bigger, or it could be the same, but it's never going to be smaller. Some clue words for knowing when to use a binomial formula is usually something, maybe it's like out of. Again, you want to go back to that binary, independent, fixed number of trials. So if it, if you see some clearly, like, hey, we do 12 trials, we buy 6 tickets, and there's an 82% chance that we are a winner or something like that, that's a probability of success. Okay, so let's try one of these. A certain kind of lottery scratcher has an 8% chance of winning. We buy 6 tickets. Assume independence. That is, every ticket we buy, even though they're in order, there's an 8% chance that we have a winner. What is the probability of no winning tickets, 2 winning tickets, 2 or fewer winning tickets, at least 1 winning ticket? Great chance to pause it. Try this one on your own. Okay. You didn't pause. You didn't do it. You just want me to do it. Fine. All right, so A, the probability of getting no winning tickets. A couple ways of doing this. We could binomial this, but it's actually simple. Since there's a 92% chance of not getting any tickets, winners, and we're doing that 6 times, it would be 0.92 times 0.92 times 0.92. So that's going to end up being 0.606. All right, part B, what's the probability of getting 2 winning tickets? So this is exactly 2. This is going to be a binomial PDF. Binomial PDF, and in this case, all right, if this was a free response problem on your AP test, you can't just put 6 comma 0.08 comma 2. You need to just write something like n. You need to let the reader know that what values you are putting into the equation, and just putting 6 comma 0.08 is not going to suffice, because, you know, is that number 6 the number of successes, or is that number failures? In fact, your calculator might use this number x instead of r, but same deal. All right, so if you forgot where that was on your calculator, it's under second vars, under distribution, and it's down just a little ways. Binomial PDF, trial 6, probability success 0.08, x value 2, paste. I got 0.0688. C, 2 or fewer. So this is 2 or less. This is going to be a binomial CDF. And I'm going to end up using the same numbers as before. So all I change is essentially PDF to CDF. And by using this function, it's going to give me the probability of getting 2 or fewer. So 6.08, x value 2. And again, this number should be bigger than 6.8%, because I could have gotten 1 or 0. And in fact, 2 or fewer, there's a great chance of getting 2 or fewer. In fact, a 99.14%. All right, what about the probability of getting at least 1 winning ticket? Did you get that one? At least 1? Remember the at least 1 rule? What's the at least 1 rule? Yay, 1 minus the probability of getting none, right? We actually we already found the probability of getting none is that. So the probability of getting at least 1 winning ticket is 1 minus the probability of getting no winning tickets. It's the complement of getting that, so that's going to be, I don't know, 0.3939. Good problems, right? Okay, last part of the lesson, good news. Geometric probabilities. This solves for finding the first success in the kth trial. And the idea with the geometric, the trial sizes are not fixed. This is going to be the big difference between geometric and binomial. Binomial, there's a fixed number of trials. I bought 6 tickets. You didn't buy 5, you didn't buy 7, you bought 6. So geometric, we're usually looking for what's the probability of getting the first success in some number k trial, the kth trial. So what that pretty much means is that you got a whole bunch of failures and then you got a success. In fact, how many failures? You got k minus 1 failures, and then you get 1 success. I'll be honest, I don't really even use the formula that much. I just think about that exactly, in this sense. So this is the formula that you will see on the AP formula sheet. It's 1 minus p k to the power of k minus 1. That's all your failures times the 1 success at the end. So this is on your calculator. There's, just like binomial PDF, there's geometric PDF and geometric CDF. Geometric PDF would solve for your first success on that exact kth trial. Binomial CDF, geometric CDF would solve for the first success in k or fewer trials. Like, what's the probability I have a first winner by the 9th ticket? Some clue words in there. Definitely the word first, if you see like first success. And again, look for problems where the trial size is not fixed. How many trials, or what's the probability of getting my first winner on the 4th ticket? So in fact, let's do that. Lottery scratchers from before have an 8% chance of winning. What's the probability that we have our first winner on the 3rd buy? And then part B, have the first winner by the 8th buy. So bought 8 tickets, what's the probability you pretty much at least got 1 winner? And in fact, there is a relationship there between what we just did, but let's just do this. Alright, so part A, the probability of getting the first winner on the 3rd buy. And what that again means is that you have 2 losers. The first 2 were losers. There's a 92% chance the first 2 are losers. And then the last one was a winner. And again, you can use the geometric CDF function on your geometric PDF function on your calculator to solve that one, but I don't think that one's particularly hard, but that's just me. This one would be, though, the part B. What's the probability of having the first winner by the 8th buy? So you're saying by the 8th buy. So 8 or fewer, right? So in this case, it's the probability of getting 8 or fewer, of having the first success in 8 or fewer. In this case, you definitely want to use the geometric PDF or CDF. Yeah, CDF function of your calculator. Probability of success is 0.08, and we're looking to do this in 8 trials. And I got a smashing number of not even quite 50%, but pretty close. Round that last number up, 48.68%. Well, I got bad news for you. I'm out of slides. Well, I hope this was a good little introduction to the probability. I hope it was helpful. Again, by no means was it inclusive, but go out on your practice book right now and do a whole bunch of different style problems of these probabilities. Thanks, guys.